Hi, I'm Linyan. Our project will tackle the topic of mutual exclusion. We will first talk about the background survey we've done so far on this topic. Then we will move on to the selected algorithm and the rationale behind its choice. And then we will wrap up this presentation with a brief overview of our distributed application. There are various mutual exclusion algorithms exist, which can be grouped into the following three main categories: centralized algorithms, token-based algorithms, and the permission-based algorithms. The centralized algorithms require a central server that either maintains a first-in first-out queue or implements some locking mechanism to achieve mutual exclusion. This type of algorithm is communication inexpensive and simple to implement, yet is vulnerable to a single point of failure and has poor scalability due to server's limited bandwidth. In the token-based algorithms, there is a unique token exists in the network. Whoever holds the token is granted access to the critical section. The main thing to consider is how to transfer the token among peers. There are two possibilities: the perpetual mobile and the token asking method. In the perpetual mobile, the token travels from process to process perpetually. Nodes are generally organized into a logical ring structure to satisfy the liveness property. This method has a low communication cost, however, does not ensure the ordering condition and is fault intolerant. In a token asking method, a process sends out a request to others whenever it tries to enter the critical section and waits until the token arrives. The message could contain a timestamp to meet the liveness and ordering conditions. The nodes can also be structured as a logical tree in order to reduce communication overheads. For the permission-based algorithm, a process asks the other for the permission to enter its critical section. This idea was first expressed by the well-known Ricard-Agrala algorithm. Then the Suzuki-Kasami algorithm further reduces the communication complexity to n messages by introducing a privilege message. Maekawa proposed an elegant quorum-based concept that each process only communicates with its voting set. The intersection of any pair of processes' quorums would be non-empty to ensure the safety condition. The original algorithm was pushed forward by many others, as choosing the quorum for each process is non-trivial. Maekawa devised a straightforward procedure that groups nodes into a matrix structure and then correlates each node with its corresponding row and column. Others further introduced several suboptimal methods, such as placing nodes in a triangular configuration or using a cyclic scheme. Additionally, some techniques arranged nodes in a logical tree, bringing down the complexity to only the order of log n. One of these methods is chosen for this project, and I will hand it over to Yuguang and let him walk you through this algorithm.
The algorithm we want to implement is the extended quorum-based algorithm. This algorithm keeps a logical structure of binary tree. For example, here is a binary search tree with 7 nodes. We start from the root to find a path to the leaf node and keep that path as a quorum. So we get 4 quorums here: 124, 125, 136, and 137. And each of them has an intersected node. And when there is a failure, let's say the root fails, this algorithm selects an alternative quorum, which are 2436, 2536, 2437, and 2537. And each of them also has an intersected node. If number 1 and number 2 fail, the quorums are 45636, 4537. If number 1, number 2, and number 3 all fail, the quorum is 4567. Here are the differences between the quorum-based algorithms. The majority algorithm needs at least over half responses from the voting set, so as the time complexity is big O(n), and it is tolerant to failure. The Maekawa algorithm controls the message communication in big O square root of n. However, it is not tolerant to the failure in the requesting voting set. The extended quorum-based algorithm keeps the upper bound of communication overhead in big O log n in the best case, benefits from its binary tree structure. It is tolerant to failure, even if that may increase the overhead. In the worst case, the time complexity is big O(n). However, it is an extreme case, only if all the no-leaf nodes fail. The application we want to implement is a distributed file system for a single file. Any node can read it concurrently, but only one node can write to it at a time. In this project, we will implement this algorithm to make sure the consistency of the data. And this is our reference list. Thank you for listening.